Continuing our exploration of chemical kinetics, we're going to be talking about the differential rate law. Now, just to remind you, kinetics answers the question, how fast does a reaction occur? We're looking at the changes in the amount of reactants or products per unit time. The usual unit is molarity per second. Now, rate laws are a mathematical method for determining how fast a reaction occurs when a certain set of circumstances are given. And there are two types. The differential rate law, which is sometimes just called the rate law, and that calculates how fast the reaction will occur based on the initial concentration of the reactants. The integral rate law calculates the changes in concentration as related to time, and we'll deal with that in another video. So for a typical reaction where R plus S makes some products, the rate law would be rate equals K times the concentration of R raised to the power of M times the concentration of S raised to the power of N. The rate law always deals with reactants. Now, K is called the rate constant. M and N are typically small whole numbers, usually 0, 1, or 2, occasionally 3. M and N are called the order of the reaction in respect to X, and if you add M and N together, you get what is called the overall order of the reaction. So you may be told that the reaction for 2R plus 3S becoming R2S3, the rate law is rate equals K times the concentration of R times the concentration of S squared. You would say the reaction is first order in respect to R, it is second order in respect to S, and the overall reaction is 1 plus 2, so it is a third order reaction. Here's a different reaction, and the rate law is rate equals K times the concentration of Q. This is first order in respect to Q. It is 0 order in respect to J. Remember, anything raised to the 0 power is equal to 1. And the overall reaction is first order. Now, you may have noticed that the rate law is not stoichiometric. The coefficients might be the same as the powers M and N, but they do not have to be the same. And K is a constant, but is only constant for specific temperature. If you change the temperature at which the reaction occurs, you will change the value of K. K is just constant for a specific temperature. And when you're calculating the value of K, you will need to use dimensional analysis. Here is a very important rule. The rate law must be determined experimentally. How do we do that? The best way to do this is with an example. So let's take this equation, and you would be given a data table that looks something like this, where you're given the concentrations of the reagents and what is called the initial rate under those conditions. You set up the generalized equation, rate equals K, in this case the ClO2 raised to the M, the hydroxide raised to the N. Look at the experiments and pick 2 experiments. Where possible, ideally, set it up so that one reagent doesn't change in the 2 experiments. So in this case, we're going to pick the first 2 equations because the hydroxide stays constant at 0.030 molar. Now you're going to set up a division utilizing the rate expression or the rate equation, putting the highest rate on top. So the highest rate here is 0.0248 molarity per second. So you set the equation up so it looks like this. Now notice the K's cancel out and the 0.030 raised to the end cancel out. So what you're left with is 0.0248 divided by 0.00276 and 0.060 divided by 0.020 raised to the M. When you do that math out, you get 9 equals 3 raised to the M. So what number do you raise 3 to get 9? You raise it to the second power, you square it. So the value of M has to be 2, and you can put that in up there. So now we're starting in this condition, but we know that the order of the reaction with respect to the ClO2 is 2. You do the same thing for the hydroxide now. We're going to pick 2 experiments. If it's possible, you try to make sure that the other reagent cancels out. That may not be possible, but that's okay. Here we'll pick the bottom 2. We set up our divisions of the rate expressions, putting the higher rate on top, and now it looks like this, and you can see that the K's cancel out. and the 0.020 squared cancel out. When you do the math with what's remaining, you get 3 equals 3 raised to the n. So n must equal 1. So we can change this and put the 1 over here. But since we usually don't write to the first power, we would say the rate law is this. It is second order with respect to the ClO2. It is first order with respect to the hydroxide ion. And the overall order is third. So let's do another one. Here we have nitrogen monoxide and oxygen becoming nitrogen dioxide. And here's the data. Here is our generic rate law. We're going to pick the first two, plug it in, set up our division, putting the higher rate law in the numerator. You get 4 equals 2 raised to the m. So once again, m must equal 2, and we can put that up there. So now we deal with the oxygen. We're going to pick the bottom 2. We set it up, and in this case, we see that it doesn't really matter which one goes on top because they're the same. We set it up. The k's cancel. The 0.0252 squareds cancel. When you do the math, you get 1 equals 2 raised to some power. So n has to equal 0. And so we can put the 0 next to the O2, but anything raised to the 0 power is 1. So we would say the rate equals K times the concentration of the nitrogen monoxide squared. It is second order with respect to nitrogen monoxide. It is 0 order with respect to the oxygen. And the overall reaction is second order. But you then may be asked, what is the value and unit for K? All you have to do is pick an experiment, plug the values into the equation, and then solve. And in order to get the unit for the rate constant, you have to use dimensional analysis. Let's pick the first experiment. The rate, 1.41 times 10 to the minus 2 molarity per second, equals K times 0.126 molarity squared. Now you've plugged, now it's time to chug. You square the 0.0126, and you get 1.5876 times 10 to the minus 4th molarity squared. Divide both sides by that number, and you'll get the value for K. And when you do your dimensional analysis, you see that you've got molarity divided by molarity squared. So you're going to end up with 88.8 over molarity second, which can also be written as 88.8 molarity to the minus 1, second to the minus 1. So here is one for you to do. What is the rate law? Figure it out. I'll give you the answer, then walk you through it. Go. And the correct answer is the rate is equal to K times the concentration of the S2O8 1 minus ion times the iodide ion. So set up your generic equation, pick two experiments where something cancels out, put the higher rate on the numerator, the lower rate in the denominator. The K's cancel, the 0.036 raised to the n cancel. When you do the rest of the math, you get 1.5 equals 1.5 raised to the m. So m must equal 1. So now we can put the 1 where it belongs, and we can start looking at the iodide. You set it up so that the higher rate is the numerator, the lower rate's in the denominator. You cancel out what can be canceled out, do the math on what remains, and here you get 2 equals 2 raised to the n. So obviously n equals 1. You put that in up there, but once again we don't write the ones. So we would say the rate is equal to K times the concentration of S2O8 2 minus times the concentration of iodide ion. So we can put that under the knowns. What's the value of K? Figure it out, come back, and we'll go through it. Go. And the correct value is 0.25 molarity to the minus 1, minutes to the minus 1. How do we get that? Well, we take a look and say we can pick either experiment 1, 2, or 3, plug the numbers in, and solve. So I decided to take experiment 3. I plug the values in where they belong. I go ahead and begin to solve it. Divide both sides as appropriate. I end up with 0.25 molarity to the minus 1, minutes to the minus 1. So we know at this temperature, this is the rate law. What's the initial concentration of iodide for question 4? Stop, figure it out, come back, and double check your answer. The correct answer is 0.077 molar. Basically, you're going to take the values from experiment 4, plug, and chug. So you plug your values into the equation, and then you just begin to solve. And after you have set up your final equation, you get 0.0768 molar equals the concentration of iodide, and in correct sig figures, 0.077 moles per liter is equal to the iodide ion concentration. So to review, rate laws are just a mathematical method for determining how fast a reaction occurs with a given set of conditions. There are two types: the differential, how rate changes with concentration, and the integral, how rate changes with time. The differential rate law is frequently just called the rate law. The generic rate law is rate equals k, a to the m, b to the n, where k is the rate constant. It is only constant for a specific temperature, and the unit will vary depending upon the values for m and n. The subscripts m and n will be small whole numbers, usually 0, 1, or 2. The value of m and n must be determined experimentally, and those values are not stoichiometric. M and n are called the order of the reaction in respect to x, and the sum of m and n are called the overall order of the reaction. To determine the differential rate law, you have to compare separate experiments in which initial concentrations and rates are given. To determine k, you plug and chug the data as appropriate, and that's the differential rate law. In our next video, we'll continue on into our investigations in kinetics.